Hi, we're Team B0, and this semester we focused on creating a seamless autonotator. So, to necessitate why we need an autonotator, we can see on the right-hand side an example of how two professional players record a chess game. In a tournament setting, players are required to write down the move after they play a chess move on the board. However, since handwriting is involved in this process, we can see a very faulty, very flawed example on the right-hand side over there. Notation and the act of recording a chess game, however, can be very useful. Players can look over the notation to see their errors and see where they had gone wrong during a game. Furthermore, in the case of a dispute, tournament directors use notation as a record as to see what happened during the chess game so that they can replay the game. Since notation is so useful, but it's in such a flawed system right now, we wanted to create a system that would make it easier for chess players to notate. Our solution then was to create a chessboard which would automatically write down the moves for you. In order to satisfy this, we created a set of requirements that would match our end use case for tournament players and casual players to be able to automatically record their chess moves. On the left-hand side here, we can see that our first and most important requirement is accuracy. We want it to be 100% accurate, because if we recorded the wrong move, then the entire purpose of our notation would be messed up. Second thing is, we wanted chess players to be able to see if their move was legal or illegal in a quick time span. And we chose to use 300 milliseconds as our time frame because that's the typical human reaction time. A time that is less than 300 milliseconds would be perceived as instantaneous. For our battery life, we imagined that one of the most popular use cases would be, again, tournament play. We wanted players to be able to take this board and move it to a location which possibly could be devoid of a charging spot. And therefore, then, we wanted our battery life to encompass that of a regular tournament day, which should be under 10 hours. And finally, we wanted to add some software to this package so that players can analyze and look over their previous games. Here, we can see that we wanted to store at least 10 games, and we wanted to be able to export those games over to chess.com for analysis.
Based on our requirements, we decided to use magnets as our method of sensing chess pieces. So on the right, you can see a picture of a chess piece that has a little plastic spacer on the bottom, and inside that space there is a magnet. And then in the bottom picture, you can see how our sensing stackup works. So on the top, on the chessboard, we have a piece with a magnet in it. And then under the chessboard, we have a circuit board that contains sensors that sense what kind of piece is on top of it. This is a close-up of the entire board. So you can see that under each square of the chessboard, there's one sensor, and these sensors all get fed through multiplexers, which help select which sensor the computer wants to talk to, and then sends all this analog data into an analog to digital converter that converts all this data into something that is usable by a computer to compute things about the game state, and what needs to happen next. And this is just a higher level view of the entire hardware architecture. So in the diagram on the left, you see the full block diagram of the system. The left portion of that diagram contains all of our sensors, the multiplexers, the analog to digital converter, and its interface with the Raspberry Pi, which is our main computing unit. And then on the other side, with the Raspberry Pi of the diagram, you see the general purpose I/O that controls the user interface. This contains 2 buttons and 4 LEDs. And that's used for allowing the user to communicate with the computer, letting it know when their turns are done, and the computer lets the player know using the LEDs whether their moves are legal or illegal. The other major part of the full hardware architecture is the power. Because as in our requirements, we said we wanted to have 10 hours of battery life. So in our design, we integrated batteries under the board, and the board also has internal power regulation, so it is fully self-sufficient and does not need a wall outlet. These are just more pictures of the full custom board. And the top left is a closer view of what the sensors look like and the multiplexers. The bottom images on the left and center show the underside of the board. Here you can see all the battery storage and the power regulation. In the top right, you see this the full setup again, where the PCB is under the top of acrylic, and the pieces sit on top of that top layer of acrylic.
So we only want to notate legal moves from the board. And for that, we have a legality checker running on the Raspberry Pi connected to the board. So when a user presses a button on the board, the program will read every sensor on the board, compare the new board state that it read to the old board state, and from that, figure out the source and destination squares of the move that was just played, and then compare that move against the pre-calculated legal move list that it determined with the Stockfish chess engine. If that move was legal, it'll translate it into standard algebraic notation and send it to the website, light up the green LED and just wait for the next player to move. And if it's illegal, it'll light up a red LED and wait for the move to be corrected. And we have a video showing this in action. So first we'll play a legal move. And after the button is pressed, the light will be green. And we'll play another legal move. And then a third legal move. And then we'll play an illegal move. You can see that the light turns red. And then after a mishap with the magnets, we correct it to a legal move and the light goes back to green.
So here we can see our finished software product. And we can see on the left-hand side here, we're able to see the moves displayed in standard algebraic notation. Standard algebraic notation is the typical way that chess players record game's progress during a game. And so this is what was shown in the handwritten page on the first page, on our use case page. Here, we have options to download the game and finish the game. And we can see that we can view the list of the 10 previous games that the user played. In this, we developed the concept of a game, which can have one owner and can have many participants. This allows different users to be able to access games that they were able to receive through sharing. However, the game owner has the right to terminate a game when they deem it complete. We decided to implement our our website using Django as a server framework, and we needed to find a way to constantly update the page. This way it would display all of our notation in real time. So we used asynchronous JavaScript with XML to do asynchronous updating. Furthermore, we decided to use SQLite as our in-file database to view our past games. Finally, we sent data from the Pi using requests, and we used GET requests to transmit the data. And we deployed our website on REPL. Here is a video displaying our entire system front to end in action. See a move being played. And within a reasonable span of time, that move's notation is updated on the website. Another legal move is played, and again, within a reasonable span of time, we see that move's notation being played on the website.
So after we had built the system, we needed to test all of it to make sure that we had met our quantitative requirements. So for the notation and latency, our requirements were that we want 100% notation accuracy, because if it's not reliable in its notation, then it's not effectively useful in replacing human notation. And for the latency, we want less than 300 milliseconds of delay from the button press to the LED response. So we met our accuracy goal. We tested it with 3 unique games that had over 40 moves, and they targeted all legality cases, like all the unique edge cases of legal chess moves. And we found that our sensors always accurately detect the pieces as long as they're within 3/8 of an inch of the center of the square. The latency was tested by recording those games with high frame rate video and being able to look at the individual frames of the video where the button was pressed to when the lights turn on. That's how we timed it. And we found there that the typical latency was less than 5 milliseconds, which was very fast, but some moves were slower. It was about 1 in 30 moves that had very long latency. of like 2 to 5 seconds. And we believe that this delay was due to system processes on the Raspberry Pi taking precedence over the legality check or the firmware. And since none of us have a strong OS background, we weren't really able to diagnose this further.
Yeah, for our third requirement, which was a battery life of 10 hours, we looked at some power testing. So our calculated estimate as to what our power usage would be is around 8 watts. And with a power supply, we actually tested it and it was right around 8 watts. So that means that the batteries we plan to have under the board, which is 2 series 4 parallel of lithium batteries, would be enough for 10 hours of play. The board can actually hold double that capacity, so we theoretically could equip the board to run for a full 20 hours of gameplay.
So these are the test results tabulated. As we said before, the accuracy and the latency met our tested values with 100% 5 milliseconds. The battery life there, we could reach up to 20 hours, which beat the requirement of 10 hours. We're able to store 10 games on the website, and the website is also able to export PGN files to chess.com for analysis.